Okay, we'll start with the first and most obvious question. What
Uh-huh.
is what is physics? You have talked
Well,
about the golden principle of physics. Tell us about that too.
yeah, well, the golden principle. I'm saying that physics, first of all, physics is not the study of this or the study of that. Anybody can study and not be able to explain anything. I think science, let alone physics, but science is not just the study of something, it's explaining something. Especially as it regards to physics, you have to explain physical mechanisms, causes. That's what I think physics is about. In order to explain causes, you need to have objects. And I think the bread and butter of physics is this word called object. And to me, it's stunning that no one has figured this out in mathematical physics since the days of Newton, at least. No one has figured out that you need an object to do physics. Once you cover that step, you've got to define the word object. And no one has defined the word object in a scientific way, or not a single book in physics, textbook of physics on planet Earth begins by saying this is an object, and this is what we're going to do with it. In other words, specifically define key words that you need for the foundations of physics. This is an object. This is distance. This is location. This is what we mean by motion. These words have never been defined in a scientific way. In fact, Newton said he didn't know what motion was. And yes, I think physics is the study of causes and mechanisms. It's not about math. It's not about measuring. It's not about equations. It's about explaining a mechanism. You want to explain how a magnet works. You want to explain how gravity works. And in order to do that, you need objects, and you need to define what an object is. So that's, in a nutshell, what my vision of physics.
Okay, so how would you define an object then?
Well, if you look up in the dictionary, you'll find definitions of ordinary speech, not scientific definitions. In other words, not one that you can use consistently, rationally. And in order to use that word consistently, scientifically, rationally, you have to define it as that which has shape. That's the only property all objects have, whether imaginary objects or real objects, existing objects. All of them have the same property, shape. And what doesn't have shape is known as a concept, essentially.
Right, I agree. Okay. What is mathematics and how does it relate to physical objects? For instance, when I talk about the number three, when I talk about numbers, how does this concept relate to physical objects? I thought you'd like this one. I thought you'd like
Yeah,
this
I
one.
love the question. I love the question. No, I'm saying mathematics has nothing to do with physics or with science. And people immediately say, "What are you saying, Bill? You're crazy. What do you mean mathematics has nothing to do with science?" And we go back to the definitions and just follow them strictly. What is science about? What is physics about? If physics is about explaining phenomena, causes, mechanisms, we have no use for mathematics whatsoever. So, in that sense, mathematics has absolutely nothing to do with physics or with science if physics is about explaining causes and mechanisms. Now, if obviously, if you define physics as, measurement, equations, predictions, and, observation, proof, evidence, well, then, yes, then you can bring mathematics in. And that's what's happened. What's happened is the mathematicians have defined what science is, what physics is, not the physicists. And the physicist, a real physicist, a genuine physicist, defines physics a little different than a mathematician. He defines as that which, as causes and mechanisms. And for that, we have no use whatsoever for mathematics. Because, what does an equation do? An equation is just a description. And I'm not asking for a description. I'm asking for an explanation. And for that, you need to define the words explain and describe and find out what the difference between those two words is. A lot of people think they're synonyms.
Okay, so how would you describe these words and the difference between them then?
Well, a description is a listing of properties. I want to describe a chair, and I say it's got 4 legs, it's brown, it's big, it's small. I use adjectives and I qualify it. And all I'm doing is describing. I haven't explained anything so far. An explanation is revealing causes and mechanisms for phenomena. In other words, something happened, and you're going to say how it happened, meaning not a description like, yeah, it fell down. It fell at 9.8 meters per second square. No, that's not an explanation. I want to know what caused it to fall down. Why did it fall down and not up, for example? Or how does a magnet attract another? I can't just say, well, it attracted at such and such speed at such and such distance. That's not an explanation. That's just a description. And what I want is an explanation. I want to know the mechanism. Like if I want to explain to you the mechanism. I use this example because I guess everybody can relate to it. A pulley. You have a bucket, you have a rope tied to the bucket, and the rope goes around the pulley, the little wheel. And you say, well, how did he pull the bucket up there? It was full of water, and how did he pull the bucket up there? And I show the movie. I don't even have to explain anything. I can just show the movie, all objects there, all visible. And you see this guy pulling on the rope goes around the pulley, and the wheel turns, and the bucket goes up. And so everybody looks at that and just say, oh, I understand how the bucket ended up there. He just pulled on the rope. And that's the mechanism everybody can understand because everything is visible. Everything is visible in front of your very own eyes. And so all you got to do is watch the movie and say, I understand the mechanism. And we don't do that with magnets. We don't do that with gravity. We don't do that with light, with the atomic behavior. We don't do that with electricity. What we say there, we say, oh, let me describe it for you. And in the case of gravity, they say mass. And mass is a concept. It's a mathematical concept. I can't say mass did this and mass did that. It's like saying weight of an elephant did this. The weight squashed the ant. No, it was the foot of the elephant that squashed the ant, not the weight. Weight has no power to do anything. Weight is a mathematical concept. Likewise, mass is a mathematical concept. And you can't say energy because that's another, mathematical concept. And the problem we have today, we use these words field and force and time, and nobody has defined these terms. They're concepts, obvious concepts, and they use them as physical objects. They tell you, oh, time was warped. Oh, energy, we sent energy. We transferred energy. We moved the mass. The force was strong, very strong force, or whatever. And so we're using all these concepts as physical objects. We've gotten so used to it because they're all mathematical concepts, and it's mathematicians who have defined science, not physicists. In fact, if you go back to square one, we go back to Aristotle, and he's the guy who wrote the first book of physics that we have today, extant book of physics, and that's his eponymous book known as Physics. And Aristotle says, look, mathematicians do angles, numbers. That's mathematicians. Physicists, they do causes. And a lot of people criticize me and say, well, Bill, you want to go back to the days of Aristotle. And they have to understand the context. The context is not that we want to go back to Aristotle in the sense that, maybe his scientific method was to be desired. The issue is that he had the right idea. Physicist explains causes. That's what we forgot. There's nothing wrong with people doing experiments. There's nothing wrong with people doing math if they want. But when they come to the conference, they have to explain the mechanism. And that's what they forgot about. They do a lot of math. They do a lot of descriptions, equations, numbers. Talk about infinities, bring all these fancy words like energy and field. And what we're missing is the explanation of the mechanism. We still don't know how a magnet attracts another or how gravity works. And this is the issue. That's why I go back to Aristotle only on the issue of the notion, the context. And that's physics is about causes and mechanisms.
Okay, I think you've answered this one. Okay, we'll skip this one. What do you think the proper relationship between math and physics should be?
None. None. And again, I'm saying it's none because big if we define physics as causes and mechanisms, we have no use for math. We have no use for equations. An equation cannot tell me how Mother Nature does her secret, tasks every day, how she does magnetism, how she does gravity. It doesn't tell me that. Mathematical, an equation can only describe it and say, look, it's done at such and such speeds, so much time, that sort of thing. But it cannot tell me the cause. It cannot tell me the mechanism. And if math has no power to do that, math has nothing to do with physics. That's why it's important to define what is physics about.
Okay. What do you say to those who think? What do you say to those who say that science is all about prediction and not explaining stuff? People do say that, of course, and I know you're going to disagree with that.
It goes back to that same definition. Why did the word prediction enter the world of science, the world of physics? Well, because mathematics can predict. Okay, nothing wrong with that. I mean, we're saying that if, like I use the example, car goes at 50 miles per hour. Okay, well, you can predict that in 1 hour it'll be 50 miles away. That's straightforward, right? And so there's nothing wrong with any of that. It's predictable. The question is, we still don't have a mechanism. We don't know why the cheetah is running at 60 miles per hour or whatever. We don't have the mechanism. What we have is a description, and that's all that a prediction is. A prediction, I'm not saying that, like I'll give you an example. I can predict that tomorrow at 2 o'clock, there's going to be an eclipse. Okay? So it turns out that you wait till tomorrow, 2 o'clock, and effectively you have an eclipse. So I predicted the eclipse. What did I say? I say something's going to happen. What's going to happen? There's going to be an eclipse. So far, I have not explained the reason, the cause. All I have done is describe that this is what's going to happen. I still don't know why it's going to happen, what caused it to happen. All I know is that it's going to happen. That's a description. If you can explain why, what causes an eclipse, now you're talking about the past. You're no longer talking about a prediction, which has to do with the future. You're talking about an explanation, and you can only explain a consummated event. What am I saying? I'm saying that this guy has already, the guy who does this prediction and can explain why it's going to happen, he's already had some experience with this event. He saw it in a movie, maybe he's an astronomer and watched eclipses in the past, so he can explain why. He said, well, what's happening is the moon goes between the sun and the earth. That's why. That's why the sky goes dark. So now he's already had experience with it. We're talking about the past. We're talking about a consummated event that he's now regurgitating. That's why he can explain it. If he cannot explain it, if he can just predict and say it's going to happen, all he has is a description. There is no explanation up to that point. We have no mechanism.
Okay. Okay. Some people have accused you of being hostile towards math. Would you like to comment on this? I hear this a lot myself.
I've done gazillions of math courses in my life, so I'm very well versed in math. I just abandoned it because I realized math only gets in the way. And so I have no problem with math. I do understand math. I consider myself a pretty good mathematician. I have this natural knack to do calculations in my head. I rarely use a calculator. And, it's just one of those things I'm good at just by birth. I've always been mathematically inclined in that sense. I just don't use math because I do physics now, and I see that math only gets in the way. And so in that sense, again, I go back to the definition of physics. What is physics about? If it's about mechanisms and causes, we have no use for math whatsoever. And people have a hard time understanding that because for 400 years, at least since the days of Newton and even maybe before with Galileo, they've been harping on math and they've been harping on measurement. And I'm saying math and measurement have nothing to do with explanations of causes and mechanisms. That's the relation.
Okay. Uh, please tell. I think I can. I think you're gonna like this one. Please tell us about your views of quantum theory and relativity.
Uh,
I think you have a lot to say on this.
do you really want me to say something? Well,
You can be you can say whatever you like.
okay. You have to keep in mind first, at least the way I understand it, since the 17th century, the so-called scientific revolution, I think these people were genuine, the original people, that you look up in those days. You have Gilbert, you have Torricelli, all these people did, Otto von Guericke, all these people did experiments. And why did they do experiments? Well, partly because they were studying nature. They were trying to figure out, how this universe works. And they say, oh, look how interesting. Look at this effect over here, static electricity. Oh, look at this other one, light. It refracts and so on. Okay, fine. I think they were originally trying to get to the bottom of things, trying to explain how this universe works, in a rational way, in a way we can all understand. And again, I go back to making movies. You got to be able to visualize the mechanism. I think they were interested in doing that, but they couldn't figure it out. And we lasted like that all the way to the 19th century, end of the 19th century, all the 1800s. And when we came up with quantum at the beginning of the 20th century, 1900, Mr. Max Planck, after that we abandoned slowly, gradually, and more so to these days, we abandoned what we call today classical mechanics, which is, think of it as rational mechanics. People trying to answer, what causes things. How does this universe really work? And we got into quantum mechanics and we got into general relativity. And what do? Well, I say that the word quantum doesn't mean packet. It doesn't mean bundle of energy. I say the word quantum means irrational. That's what it means. Every time someone says quantum mechanics, he's saying irrational mechanics. Why? Because all the explanations, without exception, out of quantum mechanics are all irrational. They all have the movement of concepts. That's one problem. The other problem, probably just as bad, is they tell you mechanisms that are clearly irrational. A particle can be at two places at once. Now, what sense does that make? And the worst part is that, the mathematicians who subscribe to quantum, they say, oh, we know it's irrational. In other words, they say it in a different way. They say, we don't understand how quantum works, how that subatomic world works. We just theorize. And their theories are all irrational. Their physical interpretations, their mechanisms are all irrational. A particle can be at two places at once. You have what is called entanglement. This particle over here can affect this other particle over there, and there's nothing in between. It just does it by magic, spirits or whatever in between. And they have all these irrational explanations. General relativity, very similar. Why doesn't the Earth fly out of the solar system? Because you have this thing, very quotations on that thing, called space-time, four-dimensional space-time. Four-dimensional? What is that? I can't picture it. Oh, no, don't try to imagine four-dimensional space-time because nobody can. We have this three-dimensional mind. We're these puny little humans, and we have no way of seeing this immense four-dimensional object, whatever, that we're in. And when you say, well, hold it, time is a concept. And space, if it's an equivalent with nothing, with vacuum, it's also a concept. And so we have two concepts and we make an object and we live within this unimaginable object. And so again, both general relativity and quantum mechanics have only irrational explanations. Black holes, dark matter, conveniently invisible, conveniently heavy, conveniently sprinkled wherever you need to explain something involving mass. And you say, well, is this the way the universe works? And that's when you start doubting, the physical interpretations of these two, I'll call them disciplines so that I don't offend them and call them religions. They don't have rational explanations. And that's my take on quantum mechanics and general relativity. They have no rational explanation. We still don't understand how this universe works for all those invisible phenomena, for all those phenomena in which there's an invisible mediator, gravity, light, electricity, magnetism. We don't understand how they work. And general relativity and quantum mechanics will not help you because they can only offer, irrational explanation. A particle can be at two places at once. This particle affects the other one from a distance. There's nothing in between except spirits. And space-time is unimaginable, and it's four-dimensional, and so it's all irrational. You cannot picture any of it. That's my take.
Yeah, it's basically a bunch of really, really bad mathematics, and that's about it. Do we even need to talk about string theory? That's, as Paulie said, that's not even wrong. So do we even need to talk about that?
There's a couple things about string theory. The first thing is string theory has nothing to do with the rope model that I have. String theory is a mathematical theory, not a physical theory. Okay. And what a string theory is trying to do, the reason it came to be, is that it tried to merge or find some common ground, especially in relation to gravity, between quantum mechanics and general relativity. General relativity has equations related to fields, and quantum mechanics has specifically the Schrodinger equation, which tells you something about this subatomic world where the electron can be found around the atom. And they say, okay, so we have this micro world here with this macro world over here. The equations are totally different. They describe different things. How do we get them together? And so string theory came in and says, well, we're going to try to put them together. And what string theory does, or what it's trying to do, is what is known as quantization of space-time. They're trying to get the micro world of quantum mechanics, okay, into a point that is used to build four-dimensional space-time. Think of it as space-time, as we can't picture this whole thing, but what we can do is look at a little piece of space-time. So what is in this little piece? Well, let's take it all the way down to the tiniest, region that we can imagine. And that's where quantum can be put in there, because now this region can be treated with quantum effects. And that's what they've tried to do. Now, the first thing you need to understand about that is that space-time already was quantized. The bread and butter of space-time in that sense is the point. It's known as the event. Event is a point in space-time. What does that mean? It means that you can locate the happening, the occurrence, the event, something that happened within space-time. You can locate that with four coordinates. One, time, and supposedly the three dimensions, physical dimensions, length, width, and height. Really, actually, they're talking about coordinates. They're talking about longitude, latitude, and altitude plus time. They call those four number lines, which is what they really are talking about. Those four number lines, they call it four-dimensional space-time. And that's how you locate a point. What is that point? That's the point that we're going to analyze with quantum mechanics. And that's what string theory is trying to do. It's trying to merge the world of the small with the world of the big. And for this, they created the line. They went from the point to the line. In geometry, you have the point and you have the line, right? What is a line? Well, a line is a point that's moving somewhere, hopefully in a straight line. And so the bread and butter of string theory is the line. Is it a three-dimensional string or something? No, it's a one-dimensional line. One dimension, are we talking about length, width, height? Are we talking about longitude, latitude, altitude? None of those. What they're talking about is a number line. They're saying that something moves and traces a path. Now they turn that path into a line, to a geometric line. They say, okay, now this thing is one-dimensional. It's not two or three-dimensional. And we're going to deal with that line. And that's what we're going to construct our new math with. And that's essentially what string theory does. I don't know if it makes any sense, but that's what string theory does. And that's what all the equations in string theory are about. They take those paths then and they build brains with that. And that's another monster, All math, nothing to do with physics.
Don't forget all your other 9, 10, 20 dimensions. We won't go into that.
Yes, sir.
whatever that means. Okay, now to the good stuff. Now onto some of your ideas. Tell us about the rope hypothesis. Tell us about some of the great mysteries or poorly understood phenomena that it explains.
Well, the rope model, originally, when I came up with it, I was able to explain two things to my satisfaction. One was light, and the other one was gravity. And gravity came like, a second hint. I had originally came up with my notion of gravity, and that was that all these lines, if two objects come together, assuming that all these lines connected every atom, well, then as the two objects approach each other, these lines would fan out. And when the objects got farther away from each other, the lines would come in closer and act as one eventually, at a great distance. And I like that concept. Then I came up with a rope model separate, that was a separate train of thought. And that was that, you have a rope. Here I have my famous rope. I don't know, you can see it, hopefully. Okay. And what it is I'm saying it's a torsion along a rope. And if you look at a torsion, right, you can call it a torque wave. It's a three-dimensional wave along a rope, not a two-dimensional or one-dimensional longitudinal wave. It's a three-dimensional wave. And what it is essentially a torsion along a three-dimensional object. The object is simply twisting or torquing in place. And if you run the experiment at home, just tie a rope to two walls or two posts or whatever, and you hang two clothespins. Very dangerous, very expensive experiment, right? Take the grandma's clothesline, just put two clothespins there, and you move one of them. The other one moves, you could say, instantaneously. It just moves. Torsion is instantaneous. And what this tells you is that why light is so fast. If light is a transverse wave, it's slow. If it's a longitudinal wave, it would be slow. If it's a torsion, it's the fastest thing you can imagine. And so that's one issue. The other one issue is that, now we can explain the Maxwell's equations with it, because now you have what is known until today as a magnetic field and an electric field. What they've been describing all these days is a magnetic thread and an electric thread. And these two threads are twined around each other, and they have confused that with two plane transverse waves. And so I'm replacing the model right now with a rope. I'm saying it's a physical rope that connects any two atoms. So when one atom expands and contracts, it torques the rope. By torquing the rope, the signal goes to the other atom. And the good thing about torsion is it travels both ways. So both atoms receive the signal irrespective, and they're constantly receiving that at the speed of light because, again, torsion travels extremely fast. And so we can explain speed. We can explain other phenomena like C equals frequency times wavelength, the fact that frequency is inversely proportional to wavelength. The longer the wave, the fewer links you have along a given length of rope. And the more you torque it, the shorter are your links and the more links you have. And there you have frequency times wavelength, which is equal to the constant known as the velocity of light, which is 300,000 kilometers per second. So we can explain many things with it. And of course, I can also explain electricity. The merged electron shells, the whole thing twirls. I call it a serpentine. You have a whole bunch of atoms, actually molecules, but with atoms it's easier to visualize. You have all these merged shells, electron shells, and when one twirls, the whole thing twirls. And I'm saying that's what electricity is. When it does so, it swings threads that comprise the rope around itself, and that's going to be the magnetic field, which goes at 90 degrees to the electricity. So you have electricity in one direction, and you have the threads moving around the other direction, and that's going to be the magnetic field that causes a force on things. And so, it's a self-consistent model. You can explain gravity, you can explain light, you can explain magnetic field, you can explain electricity, all with the same model. It's just a different model out there. And what I always try to emphasize is that the issue is not to try to convince people. The issue is for people to understand the mechanism, which I can illustrate. I illustrate it, I show it there. What people want to believe, that's their personal opinion. The issue is that they can look at it objectively and say, okay, I understand what he's proposing. Whether you like it or not, whether it violates your religion, I don't know. That's your personal issue, but I can explain these different mechanisms, these invisible mechanisms with a single model.
Okay. What is the best experimental evidence for the hypothesis, or what experiments would you like to see in the future if they have not been done yet?
Okay. First, in science, we don't produce evidence for what I just said. The issue is not to try to convince people, and that's what evidence is used for. A prosecutor comes to the court, and he tries to persuade the jury to vote for his side of the case. How does he do it? He presents evidence. He presents maybe testimony from experts, expert testimony. He presents material things, the knife, whatever. He's trying to prove there how the person was killed. He presents evidence. And evidence is, the only purpose of evidence is to persuade. We don't do that in science. We do that in religion. In science, we just present a mechanism objectively. So I'm going to clarify that point first. Second, I'll say that if you want evidence, the evidence is every experiment we've done to date. We have already made practically every experiment that we can think of out there. We've done the slit experiment. We've done polarization, Compton effect. We have the photoelectric effect. We have all these experiments already done. Now we have to explain them. And so it's not an issue of evidence. It's what mechanism can you come and explain these different experiments that have already been done? How can we explain them objectively so that someone understands the mechanism, say, okay, I see what Mother Nature is doing here with all her invisible stuff. And all you want to do is explain it mechanistically, okay? So that people look at it objectively and say, okay, I understand it. Doesn't mean you're going to believe it. It means you understand it. That's it. That's where science dies. Then after that, you have religion. And then the final issue is that I have come up with a new experiment that distinguishes between the wave, the transverse wave, okay, and the rope. If light is a rope, it's not a transverse wave, which is simply a concept. There's no such thing as a wave. The transverse wave of quantum mechanics is a bunch of vectors. They only have magnitude and direction. If you look at that wave that they always show, you look at it closely, you'll see arrows. What are each one of those arrows? Magnitude and direction. That's all it is. It's a mathematical concept. There is no standalone object I can put on the table called wave, transverse wave. No such thing. Okay, so the rope model is different in that sense. So what experiment can we run? Well, I'm saying that there's one experiment that I don't think people have tried. I don't know anyone who's done it. And I've come up with this experiment, and it's the slit in a vacuum. That's what I call it. You take the slit experiment, and you put the whole contraption under vacuum. Why? Because quantum mechanics will tell you that if you remove material from that chamber where you're going to do this slit experiment, if you remove material from there, the mean free path is going to increase. The photons now have nothing to bounce against because you removed all the matter that was in its way. So what should you see at the end of, the slit experiment? For those who are not familiar with it, you run light, monochromatic light through two slits. And instead of seeing two lines on the screen, you see fringes, you see many lines, okay? And so the question is, how does Mother Nature do this magic? And I'm saying, let's put that whole setup under vacuum. What happens? If you put it under vacuum, now we remove matter from the chamber. That means the mean free path increases. And it means that now, according to quantum mechanics, right, the intensity should increase because there are more photons reaching the screen. reaching, wherever you see the fringes, there should be more photons hitting that area, that the intensity should increase. And you can measure that with a photosensitometer, multiplier, whatever. The rope model says something different. It says that light is relayed from atom to atom. Okay? So that means if you remove atoms from the chamber, you're reducing the amount of atoms that are relaying the signal to the screen. The intensity should go down. So I think that would be an experiment that someone who has the equipment should run and say, well, does light consist of little particles? If it consists of little particles and you remove all the obstacles, there should be a higher intensity. And a rope model says, look, all atoms are interconnected by a rope-like mechanism, a rope-like mediator. And if you remove the atoms, there's still ropes crisscrossing the chamber, but now you don't have that relay going to the screen, and the intensity should remain the same or drop. And so that's the difference between those two. The experiment would, I think, decide between those two. And it's got to be done very carefully. One thing you got to be aware of is that photomultipliers are, I use them, and they're designed to count blips as particles. And that's already against the rope model because it's already predetermined. These devices, they're already assuming a particle world. And so photomultiplier, that's why they call it a multiplier or a sensitometer, because it senses particles. It treats every blip as a particle. And that's already, against the rope model.
Okay. What kind of support does your rope model have? Have you had any success in getting any academic support for your model? I mean,
No,
I imagine it's pretty hard because it disagrees with the mainstream a lot. So I imagine there's some difficulty there. Would you like to talk about that?
Yeah, there's no support whatsoever because people don't know about it. That's the problem. And you can't get the people to know about it because it's a qualitative type issue. I'm saying, look, we can explain this universe, at least one model can, and that's the rope model, and that's I can explain mechanistically. I can explain to you on the board how gravity works with this model. I can explain light, electricity, magnetism. I can explain all this. And you don't have to take my word for it. You just have to watch the movie. I'm not going to tell you, look, it's unimaginable. It's four-dimensional. You can't see it. It's zero-dimensional like or one-dimensional like in string theory. No, I'm saying, look, I'm talking about a three-dimensional rope, just like I'm saying here. And it's invisible because it's very thin, very small, and so, yeah, you can't see all this, but here's the mechanism. Do you understand the mechanism? So I can illustrate what I'm talking about. But what happens? That's a qualitative issue. And the mathematicians for the last 100 years are already on record that there's no way you can explain the mechanism of this universe. They're already on record saying, no, this world works irrationally. Or better yet, they don't like to say irrational, obviously. They say, look, it works in ways that we cannot understand. We cannot explain how this quantum world works. We can describe it. Look, here's the equation. Here are the numbers. Here's the measurements. But we don't know how Mother Nature does. How can a particle be at two places at once? Well, I don't know. Don't ask me. Just take math and you'll understand it. That's the issue. And so what happens? The people who control the literature, the publishing world, are all mathematicians, essentially people who've been brainwashed generation after generation after generation now for the last 100 years. So what happens? I submitted articles. I submitted to Science. I submitted to Nature. And I get a polite, message back saying, well, editorial space is limited and blah, blah, blah. And we only have space, for nonsense. We have, that's not what they said, but this is my interpretation. We have space for black holes, magical black holes. We have space for dark matter. We have space for particles that travel backwards in time. We have space for being in different universes. What do you call? What is the term? Alternative realities. That's what they call it. We have space for all that, but we don't have space for rational stuff. And they think you're arrogant just because you think you can answer how this universe works objectively. And they say that's impossible. Only God knows that. And so they don't publish qualitative stuff. You read any paper in the literature today, it's all math. It's all equations. That's why nobody reads that. No one in the general public reads that nonsense, because it's all just math taken to ridiculous levels today. You read any of those papers, just equations. You don't see any pictures in there. So you can't understand any, you can't visualize anything, because there's nothing to visualize, because they're not concerned about qualitative explanations, about causes, about mechanisms. And so when you submit a paper talking about qualitative stuff, they reject it immediately, because they say, look, classical mechanics died in the 19th century. Where have you been in the last 100 years? And that's the issue. The issue is they won't publish anything that deals with qualitative stuff anymore. And there's no way to get that in there. So we get this irony where people go into Quora, for example, which is a site where you ask questions and you try to get answers. And 99.99% of the people go in there that ask questions of physics, and they ask questions like, how does a magnet work? How does gravity work? They want to see a qualitative explanation, and they don't realize, first, that they're asking the wrong people. Second, these people are saying in so many words, look, we don't understand how any of this works. You want to understand it? Take math courses at the university level. And so the persons, they ask a question, they never get an answer. Say, oh, I'm so puny, I don't understand any of this, and they say, thank God we have all these mathematicians that do all the thinking for us. They understand all of it. And the mathematicians are telling them in their face, we don't understand how this universe works. We can only describe it. And so we have this runaround, this is the world we live in.
Oh, God, yeah. I look at some of those questions on Quora. The answers are horrible. Well, if you want to call them answers.
I mean, you won't get an answer. You won't get an answer from any of these people. Whatever answer they give you, for sure, 120% is irrational. In other words, you won't be able to picture it. Whether it's quantum or general relativity, you will not be able to picture it. Because as soon as you picture it, they'll say, oh, you took the analogy too seriously, too literally. You're not supposed to take it. This is a mathematical description. And the only way you can put it into words is, by giving you, the warp space, the warp canvas analogy. We can only give you, particle going backwards in time. We can paint the two particles on the screen and say, look, particles at two places at once. And everybody looks and says, are these two particles? No, they're just one particle, but they're at two different locations. How can that be? Well, you got to take math to understand it. And so they give you irrational explanations. They tell you they don't understand, that they cannot explain in words because they can only express it mathematically through equations and numbers. And people are not listening to that. They're saying, oh, these people are so smart. Look, they understand all this stuff. I don't, but they must understand it because, look, they can express it mathematically. And that's what we have. That's the world today.
Mm. Okay, are there any criticisms of the rope model which you'd like to address here?
Well, the rope model is simple. Too simple for people to really say, no, I'm not going to take it seriously. This is kindergarten stuff. And it is, because physics is kindergarten stuff. Look, I always say that I like this because it's simple, and I use this. Just came from a conference in Sweden, and I showed this. And here's you see those little. If you're seeing this right, you see those two little magnets in these plastic holders, right? And you put them together, and they stick together. Okay, the very simple experiment. Now this is the entire system. The entire system consists essentially of those two little pieces of metal. That's it. That's how simple this is. Now, I ask people, do you really believe you need to take calculus at the university level or linear algebra or whatever? Do you need to take all this math to explain this simple system? Here we have just two Magnets coming together. That's the entire system. Two pieces of metal. They attract each other. You would think that all you need to do is figure out what invisible thing is here between these two magnets. I can already feel them pulling to each other. All you got to explain, or in other words, all you really got to do is make visible what you think Mother Nature has between those two magnets. And because that's the entire system. If these were the only two things in the universe, how does Mother Nature do this? And the only way you're going to figure it out is by making the invisible visible. You got to make whatever object Mother Nature's using there visible, and then you'll understand the mechanism. And I'm saying this is done with, in this case, with threads. And that's a long story, but it has to do with the rope model. You cannot do action at a distance unless you have some elongated medium, such as a rope. Then you can explain gravity and you can explain some of these mechanisms. If you're going to use particles, discrete particles, there's no way you can produce attraction, especially. I can't throw particles at you and pull you. I don't throw rocks at a donkey to pull it. I tie a rope around its neck and pull it. Then we can understand pull. But it doesn't work by throwing rocks. I've tried it, and the poor donkey ends up with a lot of headaches, a lot of bumps.
Okay. Are there any good books we can read about the rope model? I think there are a couple on Kindle. Would you like to talk about those? Or you mentioned a movie. Yeah. Anything anyone can look at to learn more. I'm sure that there are lots of people on my podcast who are interested in learning more about this. So.
Well, let me tell you something. Yesterday, I was talking a little bit about that. The fact that I used to be a Marxist at one time, and when I was the age of 17, I read Das Kapital from Marx, and that's a monster. It's a big book like that, and a lot of people get scared when they see a book that thick, and you got to be brave to read something like that. Another book is the Bible. I read it 3 times. And again, it's a very thick book, and I love the Bible, not because I'm religious, but because I like it as a historical book. And this is my book. It's another monster. It's, I don't know, is that upside down there? I don't know how it comes there. In the screen, it shows the opposite, but it says, Why God Doesn't Exist. And you can see by the thickness that it's a pretty thick book. It's 514 pages. And what's the issue? The issue here is, the entire model of the rope. And yeah, it's just not everybody can read 514 pages. A lot of those, have pictures. I have over 200 pictures because it's a very pictorial theory. You can look at the pictures and understand it pretty much. And, the words are there just to help you understand what you're looking at, right? I also have videos and so on. But the point is, not everybody reads a 500-page book in these days. Everybody wants the Twitter version, the one-liner, Tell me how this works and get it over with. And, some things are more complex. You got to know, what neutron bombardment is. You need to understand what an object is. In fact, you need to lay the foundations of physics in order to reach some of these higher level concepts. And for that, you really need to read. And people just want the quick version. It doesn't always work that way. But why God doesn't exist, and again, people focus on the word God. No, you should focus on the word exist. That's what the book is about, because physics is the science of existence. Physics only studies that which exists. And so you got to understand what an object is and what exist means. Here you have atheists and theists. They've been arguing for the last 1,000 years about whether God exists or not. Nobody can define the word exist. You look up the word exist, nobody has a definition that you can, a solid scientific definition. And I have to define the word exists for the purposes of physics, because physics is the science of existence. And that's what the book is essentially about. It talks about what exists, and I'm saying what exists is, especially all this invisible stuff that we can't see, I'm saying that's mediated by elongated objects that look like DNA. In fact, I think DNA copied its format, its structural architecture from the rope model. Which is what light is. I think it's all related there,
Okay. Who are some of your favorite physicists and your least favorite ones?
Well, again, I'm saying that we don't have any physicists. What we have is mathematicians. Yeah, you can go back in time, find people like Galileo and Newton and Leibniz and Huygens, Christian Huygens, Holland guy. And I think they were trying to get to the bottom of things. I think they were trying to understand, and that's commendable. I mean, these guys were the first people who really came out of the dark ages, you could say. They were trying to understand how this universe works, and they threw theories. They were brainstorming, and they wrote books, and they criticized each other, but I think they were trying to get to the bottom of things. And we lost that scientific spirit in the 20th century when we went into quantum. Yeah, people like Niels Bohr and Heisenberg, they tried to understand, but they took us off on a totally bogus tangent. And that's that they went in there and they said, look, let's try to imagine what's there in this little invisible world. And what is there? Particles. And today we've evolved from there and we say, well, what is a particle? And the guy says, well, it's not this corpuscle that we had in the days of classical mechanics, rational mechanics. Now we have an irrational version of the corpuscle. It's a vibrating field. In other words, the famous corpuscle of today, the quantum corpuscle, is made out of verbs, out of motion. So what is it that's moving? Well, it's just a verb. We see the verb precedes the noun in quantum mechanics. And that's where we have a problem, because it's all irrational then. You don't see the object. And they say you're not supposed to see an object. You're supposed to understand it mathematically. What we have is the vibration of an equation. You have this wave function. What is vibrating? The function. What the hell? And so, yeah, I don't have too many favorite so-called physicists, because they aren't physicists. A physicist is a guy who can explain a mechanism, not a guy who can describe it mathematically. And what we've done in the last 100 years, at least, is just describe. And so I don't consider any of them physicists. I dismiss them as mathematicians. I call them mathemagicians. They do everything with magic. Not even magic. They do it with irrational explanations. Not even magic.
Okay. Can we kind of answer that one?
Well, we can continue next week, and you can come up with more questions.
Well, you already answered some of these, so which I thought you probably would. Okay, I guess we can try this one. I think the answer to this one's pretty obvious, but. Do you think modern physics is a dead end? So-called physics, whatever you want to call it, mathematics.
Well, again, mathematical physics is at a dead end from a conceptual point of view. They cannot explain. They will never be able to explain. They admit they cannot explain, but you can divide a lot of these people into two camps. One group says, we'll never be able to explain. We don't have the intelligence to understand how this universe works, because our minds are not built to understand it, because you can say that we are stuck in this limited three-dimensional world, and the universe is actually four-dimensional, 26-dimensional, whatever. It's beyond our comprehension. We'll never be able to understand how this universe works. And then there's the other group says, well, keep sending the money, and we're going to investigate, and someday we'll understand. And so I think that's how mathematical physics is divided today in these two groups. And, it's just they're at a dead end in that sense. They cannot explain gravity, and they cannot merge the equations of general relativity with the equations of quantum mechanics. They cannot merge them. That's what string theory is trying to do. So what happens? In that sense, they're at a dead end. They say, don't expect anything because we cannot comprehend it. Physics, once we figure out physics, how this universe works, we're done with physics. There's no more physics after that. Once we understand how Mother Nature runs, or Father Universe runs his shop, we're done. We just understand and say, okay, now we understand what this universe is, how gravity is done, how light is done, how electricity is done, magnetism. So we're done. Now we understand it. We have no more physics after that. We can shut down all the accelerators on Earth. We can shut down NASA. completely in the European Space Agency and the Japanese Space Agency, Chinese, Indian, all of them. Why? We're going nowhere. We're going nowhere. We're not going to inhabit the solar system. We're not going to expand into another planet. We're not going to terraform another planet. We're not going to go to another star. There's no possibility of any of that happening. We die here on Earth. And so, again, I think we're just spending money in a lot of this stuff, simply partly to keep a lot of these mathematical physicists occupied, giving them a job. But what are they doing? They're just telling you, we cannot figure this out. They cannot figure the problem out. They don't have solutions, physical solution. They have mathematical solution, but no physical solution. So in that sense, yeah, mathematical physics is at a dead end. And with a rope model, the way I look at it is that if that's the way the universe works, we're done. We know how the universe works, mechanistically, and there's no more science after that. Once you figure that out, yeah, you can go into more detail and say, well, how does levitation work? Like you have a magnet floating over another, and you say, well, this is a special case of magnetism. How do you explain this? Well, yeah, then some people can go in there and go into deeper little things that they want to try to explain. But I think the main points, how magnet attracts another, how gravity works, those I think are covered with a rope model. And it's covered from a mechanistic point of view. You understand it, you're done. Whether you believe it or not, well, your challenge is to come up with an alternative model, mechanistic model, that replaces or that fights against the rope model without any magic. And that's the challenge, But other than that, I'm saying that one way or the other, physics is at a dead end.
Okay. Okay, what do you make of black holes? They claim to have taken a picture of one after all. Wow, a computer image of one.
Don't make me laugh. Black holes. See, people are so much into black holes, and I know this because you answer a question about black holes and you get 1 million hits. You talk about how does electricity work, you get 1 hit, 2 hits. Nobody cares how electricity works. No one cares how a magnet attracts another. But you talk about time, you talk about black holes, dark matter, man, everybody is an expert. Everybody knows everything about it. So what is a black hole? Well, you got all these bright celebrities today. Brian Greene, he's a celebrity of, poster boy for mathematical physics. Michio Kaku, another big name. Rising star, Sean Carroll, Lawrence Krauss. All these names are coming up that someone or other has heard about here or there. Just about everyone has heard about one of these guys out there. And these people, they're all black holers. They're all dark energyers. They're all dark matterers. They believe in all this stuff. So what is a black hole? What is dark matter? What is dark energy? And, these people have been interviewed and they tell you they don't know what a black hole is. And it's not surprising because a black hole is not something. It's not a what. Black hole is a concept. It's a mathematical concept. It starts out with a star, more massive than a sun, than our sun. That means it's got more matter than a sun. Because it's got so much matter, it compresses gravitationally. Okay, it's drawn into its center. But unlike a normal star like our sun, it comes to it doesn't have enough matter to squash it beyond a certain point, and it ends up being a little ball, dark ball of some kind, right? But a black hole is a star that is so big it just continues compressing. And listen carefully. It compresses until it crushes all matter out of existence. There is no matter. What it does is crushes all matter to a point, a zero-dimensional volume. There is no structure left, but this structure has lots of energy. Lots of mass. Sorry, well, energy, but it's got lots of mass. So you think of it as an elephant, which weighs 6 tons. So you crush the elephant to a point so that there's no more elephant. You got zero volume, but you still have the 6 tons. And now with these 6 tons, you move them around, you can do all kinds of magic, also through magic. You know, you can move ants around. How did the ant move? Well, it's the 6 tons here that are moving the ant over here. And you say, by what physical mechanism did it do it? And that's where they fail, because they say, well, it's done through math. You got to take a course in math at the university level to show you how mass affects something at a distance. But that's a description. You still haven't told me the mechanism of how a zero-dimensional, ultramassive object, if you can call it an object, it's really a concept, how that mechanistically affects an ant over here. And so a black hole is not a physical object. You can't bring a standalone model of a black hole and put it in the middle of the room at the conference and say, that's a black hole. Point to it. What are you going to point to? It's zero-dimensional. And then, of course, you got all those mathematicians who say, well, it's not really zero-dimensional, it's not really made of nothing. But we got a problem with that, because Mr. Chandrasekhar, who won the Nobel Prize for this, proved mathematically that a star beyond a certain weight, a certain amount of matter, collapses to a zero-dimensional volume, and it's all mass. That's what he won the Nobel Prize for. Now these people want to turn it back and say, well, you misinterpreted. You didn't understand. There's nothing to understand. He won the Nobel Prize for saying that a black hole is zero-dimensional volume that has tons of mass. That's what a black hole is. And so, you know, we have a non-object because it's zero volume. Structure has been crushed out of existence. And all we have is mass, a mathematical concept. And that's what a black hole is. And that's why no one can tell you what a black hole is. And the punchline is that it's a circular argument. Because when you go to high school, college, they tell you, well, what is mass? Can you define what mass is? Well, mass is the amount of matter, or a measure of the amount of matter in an object. And here, Mr. Chandrasekhar says, all matter has been crushed out of existence, but we still have mass. So what is a black hole? It's a bunch of mass, no matter, and then you got to define mass. What is mass? And they have all these, at least 7 definitions of what mass is out there. And you can use any one you want to make your case, and you're okay, and nobody will challenge you.
No, right, math without math. It's a big contradiction.
Of course. It's not rational. No longer rational. What is rational?
At least.
You know, it's important to define the word rational, because I'm saying that science is rational explanations of mechanisms in the case of physics. So it's rational explanations. What does rational mean? I mean, rational, Bill, is your opinion. Well, we have to distinguish good and bad, right, wrong, correct, incorrect, true, false, from rational, irrational. Rational, irrational have objective criteria. And people say, how can that possibly be? That's your opinion, Bill. Yeah, there is rational criteria. And again, you can take this to whatever limit you want, but rational criteria is as follows. The first point, you cannot move an abstract concept in physics for the purposes of physics. I cannot say that love moves mountains, not literally, not in physics. I can say that a heart moves mountains, because a heart is a physical object and a mountain is a physical object. I cannot say that a concept such as love moves a mountain. I cannot say that I warped time with gravity. I cannot say that I pushed a mass. I cannot say that I transferred information or energy. Mathematical physics only has irrational proposals because they're in the business of moving concepts. And that's the first criterion for objective criterion for irrationality. A second one is using undefined words or using words inconsistently. You have a definition here, another one there. Case in point, the word point. What is a point? Well, if you go into geometry, you go into mathematics, they'll say, Well, a point is, what is a point? And the guy says, let me show you. And he takes the chalk and hits the board, the blackboard. He says, that's a point. Okay, a dot. Well, not really. See, a point is really a location. Location? Well, really, it's a set of coordinates. So you take these two coordinates, and whatever's there at where these two crisscross, that's what we call a point. Well, what happened to the dot? Well, you're taking it too literally. You know, the point is not the dot. Don't look at the dot. The dot is there to represent the point. And so it's a circular argument. They're not using the term consistently. They're putting a dot. You understand that because you can see it. And they say, well, but don't worry about the dot. The dot is just a pictorial representation of what a point is. And so it's a circular argument. And they're not using their terms consistently. And again, you know, you'll find that they don't have a definition for the word energy. They don't have a definition for the word mass. And they don't use these terms consistently. And that's another objective criteria for what is irrational. And then a third one that I usually mention is that the theory doesn't follow from the hypothesis, from the assumptions. The prosecutor, he presents a knife at the beginning of his case. And here's the knife. He presents Exhibit 1, puts it on a judge's desk. And then he goes with his theory and he says, and the victim was poisoned to death. What do you mean he was poisoned to death? You presented a knife and you talk about poison? So the theory doesn't follow from the assumption. And that's also irrational. So there are criteria for what is rational, what is irrational in physics. Okay, and so, physical interpretations have to be rational in order to be part of rational physics. Otherwise, we have irrational, I don't call it physics, I call it religion.
Okay, I got a question for one of my listeners here. How does rope theory explain the results of Michelson's interferometer experiments? It indicated that there is no medium through which we travel. The rope theory seems like a medium.
Well, the Michelson-Morley experiment, I think you're referring to.
Yeah, that's the one. Sorry. Yep.
Okay. Michelson-Morley, they did their ether experiment. I think their final one, or the most important one, was in 1887. And what they did, they had this interferometer and they sent light in different directions, and they found out that in one direction, as well as in the other direction, it didn't matter which way the Earth was moving, etc., there was no ether wind. In other words, there was no background of what the ether is, essentially, is a bunch of particles. That's all the ether is. Everybody that mentions the word ether is referring to, directly or indirectly, implicitly, to a bunch of particles that form like a background, okay? And the issue is that, there is no background in that sense. What you have is atoms that are moving, I can't say through space because space is not a medium. Space is absolutely nothing. Vacuum, emptiness. I define it as that which has no shape. If something is that which has shape, nothing is its antithesis. It's that which has no shape. And so now we can use these terms consistently. And so there is no such thing as space, and therefore there is no such thing as ether that fills space. My universe, the one that I'm proposing through the rope model, is atoms interconnected. They're all atoms are interconnected by what I call electromagnetic ropes. That means there's this twined double thread, right? Two threads that are twined, and they connect every atom in the universe. And what happens is the atom now slides along the rope as it eats rope. And again, a picture's worth 1,000 words. If you look at my model, if you look it up there, you'll see that the rope itself makes the atom. So think of sliding a bead along an abacus. The bead slides along the wire there. It doesn't eat up the wire. In other words, it just slides along and the wire goes behind it. And that's more or less what's happening with the rope model. The atom is made of these threads itself. And as the atom glides through the rope, the rope goes around it and behind it. So the atom is sliding along the ropes at the same time it's pumping and torquing the rope. There's several mechanisms there that are going on simultaneously. And again, you would have to look at the model from a pictorial point of view so that you understand it much better than being able to explain it. So what happens is if an atom slides along, of course, there's no ether, there's no resistance. Light always travels at the same speed, no matter in what direction, no matter what material it goes through. See, we have something called refractive index, and that's important in this context. The worldly wisdom today is that when light goes from a lighter medium, from a less dense medium to a denser medium, like from air into glass or into water, we know it refracts. You put a pencil in water and you see that the pencil is broken. That's called refraction. And how does Mother Nature do that little, magic? And people say, well, very easily. Light is traveling at a different speed in this denser medium. That's the explanation we have today. And for this, we created a big table known as refractive index. For every material, we have to have a different speed of light. The rope model has a different proposal. It says, look, light always travels at the same speed from atom to atom, anywhere in the universe, between any two atoms. I don't care what the atom belongs to. If it belongs to a crystal, to metal, to water, to air, it doesn't matter. Light between any two atoms, always 300,000 kilometers per second. And that's the little equation C equals frequency times wavelength. What changes is the frequency versus the wavelength. When the wavelength gets longer, there's less frequency. And when the frequency increases, the wavelength gets shorter. And that's the equation of a rope. Here's a limited amount of rope, right? I torque it. See if I can torque it. Okay, very tight. And you get lots of links, and each link is short. Now I untorque it, okay? Now every link has become longer and we have much fewer links. In other words, less frequency and greater wavelength. And that's the equation of light. Light always travels at little c at 300,000 kilometers per second. So all that happens between any two atoms, whether they go through a dense medium, light medium, whatever, is that what we change is the frequency for the wavelength. There is no medium out there that retards light, retards the speed of light. Like, again, a particle going through some kind of medium such as water or molasses. There's no such thing. It's not a particle trying to get through molasses. What it is the torsion changes. In other words, you expand the link, it becomes longer, and you have fewer links. And so there is no ether out there that's acting as a molasses, which is essentially what the Michelson-Morley experiments, they did a series of experiments, essentially showed that there is no background, no bunch of particles. The universe is not a sandbox where light has to go through different layers of sand, more dense sand here, less dense sand here, and so on. And here you have a solid, and here you have a liquid, and here you have a gas. And so light has an easier time to go through gas than it has through solids. Why? Only because what changes is the frequency and the wavelength in each one of these mediums. There is no such thing as refractive index. As I like to say, refractive index is a Ptolemaic explanation for what light is doing. And if you know who Ptolemy was, you'll know what I'm talking about.
Yep. It is, yeah. I've always thought that, actually. And of course, there are a lot of those in physics, so-called physics these days. So I think that's the last question, actually.
Okay.
More, but you actually already covered them, so that's okay. That's okay.
Good,
Let me just
breathe easily now. I just hope they don't lynch me tomorrow. There's a lynch mob's always waiting for me outside.
Oh, thank you for that. That's great. although I might have some questions to ask, so we might do this again. Maybe we'll have some follow-up questions from from my listeners if they have any. In fact, I'm sure they will actually. So.
Okay. Well, hopefully someone is enlightened a little bit and has the curiosity to go beyond what they've heard from the establishment. And they look into this and they say, well, look, you don't have to believe in it. All you have to do is understand it. That's what I'm saying. And maybe they go out there, they understand and say, oh, this is interesting. And at least it gives them a different vision of the universe as a minimum, I think, because you won't find this in the official literature. None of this.
Oh, I have lots of listeners and people who will definitely do that. That's one of the reasons I'm doing this, so they can find out, or get a good introduction to your stuff. Even though
maybe Kiwi land is where this takes off.
Wow, maybe. So we will do this. I'll get back to you maybe, and I'll show you the product when it's out. I think when did I release the last one? I think it's due in like a week. I think that's when it's supposed to be out. So if you want, I can give you the link and you can have another listen to it if you want.
Well, I'm just worried that the people in Auckland and Christchurch and all these other places down there, that they don't come with a rope and do something else with it.
Hopefully not.